So in today's video, what we're going to do is take these donuts that we made yesterday on the turret lathe and drill them with the bolt pattern for Ford F-150. So these are our track adapters for the Ruby tracks. They're turned from 7-inch diameter, 1045 hot roll. So we're gonna clamp them down in the chuck here on the bed mill, run through our tooling to do our bolt hole patterns and our countersink and our chamfers and threads and all that good stuff. I'll walk you through the process as we do it. But the first thing I have to do is square up my chuck. I've already homed the bed, but now we got to find our center. Make sure our chuck is clocked because we've got the jaws clearanced, because we have to drill through, all the way through and out the other side of these pucks. So we had to make recesses in here, and if we don't clock this perfectly, we'll end up, interfering and hitting part of the jaw that remains. So that's going to be my first step. So my trick for that generally is I have used my countersinking tool. I've got it on a long shank here just for some of the parts that have a deep bore. What I'll do is I'll run it up the side of the jaw, back and forth until it looks like it's pretty well even. I don't have to be precise like to within 1/1000 of an inch, but long as I'm within, say, 5 thou, which I can generally see with my eye, that'll be close enough to square that we won't interfere. I don't know if you can see it there, but as I'm moving my y-axis, it's actually spinning the spindle a little bit, just rolling along the jaw. What I want to do is I want to see that it's touching at this end of the jaw and this end of the jaw. If it's touching at both ends, I know that thing is perfectly true. So now, see, it stopped spinning when it got to this end. That tells me that it's still clocked a little bit. So we'll get up to the other end and go again. There, we're spinning all the way through. That's telling me that I'm close enough. Get the Z-axis out of the way and tighten the chuck down. So the next part of the job is finding the center, the center of our axis for our program to reference. So the way I do that is, I just need to find the part. I'll be right back. So we've got this disc right here. This is my go-to for setting it. It's getting kind of banged up, but it's true on the outside. Soon be time to clean it up. I'll tighten that in the chuck, pull my countersinking tool out, and put my dial indicator in. Now you might wonder why I didn't use the dial indicator to set the jaw, and that's simply because I I don't need to be super precise in the clocking. I just need to have clearance for the tool to go through the part and not, you know, contact the jaw. So the way I did it there is just quick and easy, and it does what I need it to do. But now we got to find the center with reasonable accuracy, so the dial indicator is pretty much the only way I have to do this. This machine, now new machines will have probing capability, and this machine I believe had it, but it was also manufactured in 1997, and they don't make the anti-lamp control anymore, so those extra features just aren't available. So we'll get it by eye as close as we can, and then start swinging our dial indicator around. So right now we're in about 4 to 5 thousandths of an inch of bang on. We're within 1,000th all the way around. So I'm going to call that good. So the next thing I have to do is go into my control and set that location. Go into my offsets. I need to calibrate my X and my Y. We'll leave the Z alone. Calibrate X. Calibrate Y. Exit. So now the machine knows where that 0 is. And our program will reference that for all our other tool positions. So the next thing we have to do is put our workpiece in and set all our tool heights. Some newer machines, of course, have tool reference where maybe you have to set one tool and then all the other tools will reference that master tool, or they might have a probe that the tool will go over in contact. We do it the old-fashioned way with we put the part in and slip a piece of paper underneath the tool just to know that we have, you know, a couple thousandths clearance. That's well within reason of the accuracy that we need for this part. Our first tool will be our 27/64 drill. We'll move off center a little bit and bring it down till it contacts the part. I'm sure there's fancier ways of doing this, but I just slip a piece of paper. We know that's 2 to 3 thousandths of an inch. As soon as it starts to snag under that tool, I know I'm in the ballpark of where I need to be. We're not building We're not building satellites and rockets here, so this is plenty accurate. There, now it's grabbing. So I'll go into my tools and calibrate my Z for that tool. Now I'm on to my next tool, which will be my half inch tap. My half inch tap. It's a tension compression tap head. This machine doesn't have a spindle encoder, so it knows approximately where it should be relative to how fast it's spinning, but it doesn't know exactly. So this tension compression tap head takes out any error. We'll bring it down and touch. And that's there. Next to be my 5/8 drill. We'll shut that air compressor off for the rest of the video.
Alright, we're there, calibrator Z. We'll do that with 2 more tools.
There, now our tool heights are set for all of our tools, and they're recorded in the tool library. So now what we have to do is we'll exit out of here, and we want to load the program. Today we're doing a 6-hole pattern for Ford, which is 6 on 135. I've got all my programs listed here because it's just a quick reference. I can't put all this information in my program table. So the one I want, 6 by 135, 1 3/4 thick, would be my RT105 program, metric. So we'll pull up the RT105, go into our programs, look for RT105 and just go down to it. Actually, it's right there, RT105. Select it, exit. Now our program is loaded. One thing I like to do, because I've not run this machine in a while, is I like to just fire it up maybe for a minute. Make sure that there's make sure I didn't make any mistakes. So I'll start the program and let it just run with no tool. I just got that to contain the drawbar. So, external warning signal received. Clear that. We'll see if everything goes. And there she goes. My hand, of course, over the emergency stop button just in case. Shoot some coolant out the back. Just make sure everything looks right. We've all seen the machine crashes on YouTube and Facebook and Instagram. I'd rather not do that today. Alright, I'm happy with that. So we're going to do is stop the program. Program is stopped. Turn the spindle off. And go back to manual. Now I'm going to go grab my safety glasses. We're going to start throwing some shrapnel around. Get a different pair, I guess. And run our first tool. Shift to auto. And watch it drill. Once we get a little further into the job, I'll bring you in closer so you can see what the machine is doing. Actually, I'll bring you in now. So this machine has a variety of different programs, like for drilling, it'll have like a chip clearing cycle or a pecking cycle, and right now it's pecking. So what it wants to do is go in, take a bite, and then bring that chip out and get rid of it before it goes back in so that they don't pile up inside the hole and gall up. So that's why it's, you know, going in, coming out, going in, coming out. This material is pretty tough stuff. I think it's considered still low carbon, and it's easy to drill as long as you keep it cool. But as soon as you heat that up, it work hardens, and then it's basically a write-off. Then you got to go in with carbide tooling to cut through it. Regular high-speed steel drill won't cut it. So we got to make sure we keep our coolant on the tool at all times and make sure that our tool is kept sharp. So that's that. Take my drill and my countersinking bit and just put a chamfer on the holes before we go in and thread them. And then I just fill, they're all blind holes. So I just give them all a squirt of hydraulic oil, actually, to help prolong the tap life. So we'll put in our 1/2-inch tap and shift into low range on the head and go again. So I don't know if you'll be able to see, but if you watch really closely, you might see this sort of screw itself out a little bit, and then when the machine stops and restarts, it'll kind of take up that slack. That's the tension compression component working. Because these are blind holes, we use a spiral flute. Tap. Pulls the chips out instead of driving them in. So that's it. That's all our holes are tapped. We'll stay in low range for the rest of the job. And now we'll run our 5/8 drill down. Now you'll see with this, a bigger drill, and it takes longer to drill the holes. So we don't allow it to come out after every peck. We send it in, I think it's going in maybe 50 or 100 thousandths, making a chip. That chip is coming out. It does that a number of times, say maybe 10 times, and then it'll come out. Any chips that didn't find their way out naturally, it'll bring out and throw them away, and then it'll go in and restart the hole. We do that just to save time because it's a lot of back and forth on these bigger drills. So you can see here what I was talking about, why we had to clearance our jaws, because that drill has to go all the way through the part, and if we didn't clearance it, it would drill into the jaw and make a mess, right? So So now that we've pre-drilled all our lug holes for the vehicle, we're going to go back in with a larger drill to create the seat basically for the lug nut. The one nice thing about this mill, it's big and it's ugly and it's not enclosed. It's got a lot of disadvantages, but it's rugged, so it doesn't mind these big drills at all. But same thing, it's going to go down and it's going to peck at it and pull little bites out just like that. You can hear it engaging and disengaging. It'll do that X amount of times and then pull itself out of the hole, throw the chips away that didn't come out naturally, and then go back in for another cycle. All of that you can see. I'll take you over and show you the control. You can see the program dimensions here. The distance to go, its target, it's going to go for each cycle. Now it's moving its Y, it's moving its Z. This is the program up here. The G codes. Basically the G code is a different command. Every different G code is a different command, whether it be drilling or milling or what type of cycle it's doing. That's all built into the program from the beginning. See down the side here, I kind of have my cheat code for when I'm putting in a program. We're actually running a bit high on the feed rate right now, so I'm going to turn the feed back to 100%. 200 RPM. It's telling us how far we have to go. There's a bigger view of the actual motion happening. So this machine is running to tenths of a thousand, 4 decimal places. It's not actually that accurate because it's so old. It's got a little bit of wear. It's probably accurate to about 3 1,000ths of an inch. We're back to the main screen. We'll do another video at some point to show you how we make a program for this, but that just gives you an idea of the program running. So now all our 1 1/8" holes are drilled. The last thing we have to do is countersink these holes. But first, we want to make sure that we don't have any chips left in the hole, because the countersinking bit will just go in there and sometimes it'll get the chip between itself and the material and just scrub on the chip and not actually cut, which will, you know, damage the tool. So we'll pull all the chips out. Sometimes we can blow them out, but just easy to use the pliers and pull them out. So I'd say we got them all. This is our countersinking tool, single flute. It's got a long shank on it because we use it for some other jobs that have quite a deep hole. And it'll just go in there and put a 60 degree taper on that seat that will match the taper of our lug nuts on the vehicle. Pretty quick process. So that's that. That's all drilled, countersunk, ready to go. Normally what I'll do is I'll go through all 4 of these before I give them any more attention, but for the sake of this video, we're going to complete this part and call it good. You're not going to have to watch me do all 4 of these because it's just going to be repetition of the same thing. So we take this out of the jaws and deburr the backside again with our countersink. Real quickly, just want to take off any jagged edges that might cut your finger when you're putting it on. And then we'll get ready to put the studs in. So take a little bit of brake clean, spray it in all the threaded holes because we're going to put some Loctite in there, and we want the Loctite to adhere. Blow it out so it's nice and dry in there. You still see some residue of the coolant in there, so we'll give it another little wash. I don't know what we're going to do next year when Trudeau gets rid of brake clean on us. But we'll deal with that when the time comes. So I'm going to put it back in the chuck to put the studs in. Give it a wipe first with our rag. Put it back in the chuck. I'm actually going to deburr the edge of these big holes. Be right back. Just take our hand deburr and go around a couple times. Again, to save anybody, cutting their fingers on a sharp edge. Blow that off. And now for the Loctite, and give it a drop in each hole. Give that a chance to kind of run down. And then start our double-ended studs. We use double-ended studs for these. There's a few reasons why. Hole clearance is one. Ease of manufacturing is another. Cost, maybe another. Thread them in as far as we can by hand. Try and spread some of that Loctite around. If I'm not careful, you can see here it traps air in there, and then it tries to spit the air out, which tries to spit the Loctite out if we use too much. But it's better to have too much than too little. Wiggle it as we go down. And then we'll take my fancy little nut driver tool. This is actually a lug nut off of Ford Explorer. It was the only nut I could find that had rolled threads that were strong enough to do this job. We tried all different kinds of nuts, but a cut thread will pull out eventually. And then inside here, we actually put a ball bearing in there and welded the top so that the contact point is really small on the end of the stud, so it'll actually, you know, drive the stud in, but it won't hold on to it so tight that it wants to pull the stud back out. Generally, that's the case. Sometimes it will, but for the most part, it'll just thread back off. So right there, it's trying to pull the stud out. We'll give it a second, and then it'll come out. That's basically it. We don't worry about torquing these. That some people might have an opinion that these studs should be torqued in, but we're not actually stretching the fastener. You know, torque spec is basically stretching of a fastener so it has a clamping force, but we're not clamping anything here. We're relying on this red Loctite to hold this in securely. And once it sets, it takes a job. You're going to need to heat this part up probably in an oven or with a blowtorch to screw these things back out. They're not coming out on their own. So we'll just clean up the last little bit of Loctite and pull it out, blow it off, and there you have it right there. That's a Ruby Trax adapter for Ford F-150 6-lug pattern, turned from 7-inch diameter 1045 hot rolled steel on a 1967 Hitachi Seiki turret lathe. And then we drilled it here on our 1997 top well running Analam 5000M control. So there you have it. That's how a adapter is made.